Seatbelts, everyone! Please let this be a normal field trip. With a friend? No way! Oh.
Cruising on down Main Street, you're relaxed and feeling good. Next thing that you know, you see it. Octopus in the neighborhood, surfing on the sound wave, swinging through the stars. Take a left at your intestine, take your second right past Mars on the magic scuba. Alligator nostril, climb on the magic scuba. Spank a plankton too. On our magic scuba, stop the river of lava. On magic scuba, such a fine thing to do. So strap your bones right to the seat. Come on in and don't be shy. Just to make your day complete. You might get baked into a pie on the magic scuba. Step inside, it's a wild ride. Come on, right on the magic scuba.
Today we will be discussing the trends in the optical properties of quantum dots. Quantum dots are nanometer-sized semiconductor crystals with size-dependent optical, physical, electronic, and chemical properties. These quantum dots are roughly 10 nanometers in size and small enough to exhibit quantum mechanical properties. The sizes of these dots are unique in terms of its relationship to its optical characteristics. For instance, the band gap in the quantum dot will increase as the size of the quantum dot decreases. This causes the color of emitted light to change from red to blue as the size of the quantum dot gets smaller. This phenomenon of fluorescence occurs when the excited electron in an occupied level relaxes back down to an unoccupied level and combines with the electron hole. This bandgap energy is in correlation with the occupied and unoccupied level. The electronic absorption spectra of these quantum dots are strongly dependent in terms of size. Absorption spectra arise from quantum mechanical particle-in-a-box confinement effect, where the size dependence provides a way to monitor the particle size during growth. The dependence of absorption with respect to quantum dots can be modeled by using particle-in-a-box. In this case, the particle in a one-dimensional box is represented by the time-independent Schrödinger equation. The boundary conditions consist of length equal to L, along with the potential V of x is equal to infinity if x is less than 0, between 0 and L, and greater than L. After imposing boundary conditions and normalizing the wave function, we obtain an energy equal to h squared n squared over 8ma squared. This energy value turns out to have only discrete values, thus leading to the idea that the energy of quantum dots are quantized. Different wave functions or energy levels are specified using their corresponding quantum number. It can be noticed that the number of nodes in the wave function increases as the energy increases. Following the approximation of a one-dimensional particle in a box, we can see that by using a particle in a sphere model, we can treat the electronic properties of quantum dots. This brings the idea of using spherical polar coordinates to write the time-independent Schrödinger equation. A particle confined to a sphere will have a radius in terms of a and an infinite potential equal to 0 when r is less than a. The potential is equal to infinity everywhere else. We can apply separation of variables to obtain solutions. The solutions for the angular equations are identical to the rigid rotor of the hydrogen atom, meaning the solutions are spherical harmonics.
Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Essentially, a quantum dot is a cloud of electrons unable to move in any direction. It results from a field that electrically attracts electrons onto a given point or bidimensional surface and squeezed between two layers of insulating material. One aspect of quantum dots is shown when they are formed. In their formation, depending on the local minimum of the potential energy corresponding to the resulting quantum dot, the potential well is transformed from a normal hyperbolic into either an elliptic or parabolic well. Another aspect of quantum dots is that they follow Pauli's exclusion principle. They follow this principle when jumping from the highest energy valence band into the lowest energy conduction band. When the radii of the quantum dot becomes smaller than the exciton's Bohr radius, which is the average distance between the electron in the conduction band and the hole left behind in the valence band, quantized energy levels are observed. As the size of the quantum dot decreases, the difference in energy between the highest valence band and lowest conduction band increases, resulting in more energy needed to be inserted into the system in order to excite the quantum dot, resulting in more energy being released into the environment when the quantum dot returns to its ground state, and in the observation of a color shift from red to blue in the light emitted or in the material fluorescing.
Are you ready?
I'm ready.
Do you mind if I flip the switch?
Go for it.
Listen, it's quiet. Too quiet. It's like the calm before the storm.
Relax. This won't hurt us a bit.
Things are getting crazy.
This is gonna be nuts.
Things are getting crazy.
This is gonna be nuts. That's a bad idea.
That's what we do.
Fire in the hole!
Using the infinite spherical well model, we show the time-independent Schrödinger equation simplified by the separation of variables. This shows that the system has angular parts of hydrogen atomic orbitals, which are also rigid rotor wave functions, and it also shows that it has radial dependence. Solutions to this radial differential equation have this general form, which involves spherical Bessel functions. Using the boundary condition, which is having the radial function being 0 at the radius, we get the allowed energy levels given in terms of the quantum numbers n and L as shown here. From this, it appears we get the most important qualitative result from the solution of the three-dimensional particle-in-a-box problem. It results that the confinement energy of the particle in the infinite sphere is expected to scale 1 over a squared, or the inverse proportion to the square of the radius. Conventionally, the particle in a sphere states are labeled according to their principal quantum number and their symmetry. For example, looking at the lowest lying state, where n is equal to 1 and L is equal to 0, is the 1s state. Since the particle is confined in all three dimensions and its allowed energies are dictated by quantum mechanics, systems modeled in this manner are often described as quantum dots or artificial atoms.